Okay, so welcome to MET420, Finite Element Analysis, and we're going to meet on Monday, Wednesday, Friday, and you should have this book, and that's at the bookstore at the course pack in the back right if you don't have it already. So, and I am Professor Pringle, for those of you that don't know me. So, coursework for this class, make sure that you are looking at Canvas, that you have Canvas notifications set to alert you to assignments and announcements. The syllabus is already posted, so make sure that you're reading the syllabus so you know what's going on as far as what's to be expected and what the grading criteria are. There will be some reading, some homework. I will work on adding the schedule to the syllabus, yes. The homework, there'll be some homework. Most of it you should be able to complete in lab, but there'll be some that will require you to work on it outside of class. And then the bulk of what we're doing will be lab assignments. Make sure that you're taking notes on the information that we're talking about, concepts, ideas in class, because some of those will make it onto the test. Any questions related to the course and what we're doing? Okay, Fridays will be primarily a lab day, but there will be some instruction, and I won't specific tasks I'll video, but for the most part I probably won't video on Friday. So what is FEA? The building blocks for FEA are nodes and elements. Okay, and we'll create solutions using those elements, which will subdivide our geometry, and the nodes are the points that interconnect between the elements. The mesh is what we describe as the group of elements that are canvassing the geometry, and the solver doesn't understand the geometry. The solver understands the nodes and elements, and that's what it's working with. So our mesh, our nodes and elements, have to approximate our geometry well to be able to obtain a good solution. So the process for doing this, and much of this will be masked by the software. When they first developed FEA, these were 3 separate software packages that you dealt with and transferred files between. There's a preprocessor, the processor, and the post-processor. So the preprocessor is putting the mesh together and working with the nodes and elements. The processor is then taking the forces and the loads and determining the displacement of those nodes for each element. And then the post-processor is what is showing you the pretty pictures, right? Or giving you some tabulated information about the forces that are going on. But, you know, once you get the results, you as the engineer have to be able to interpret those and validate them, and you know that's the important part of what's happening when we're developing this. The steps that you will typically go through as it involves dealing with looking at doing a finite element problem is you have to define the problem and identify it, and maybe you do an analog calculation, and maybe that's sufficient to provide the results that you need. If it's not, then we go into the finite element analysis portion of the tree here and work through the process of developing the mesh that overrides the geometry processing it and interpreting the results and validating the results, because it's very important that we're able to validate the results. So speaking of results and pretty pictures, they're always wrong. Can never believe the pretty pictures. So why is that so? So this will be the only time that I'm going to read to you in class, but I think it's important because it cannot be overstated that the finite element method is an approximate method of analysis, and that the way an object is modeled, such as the choice of elements that represent the loading, and the method of analysis is what is going to determine how this comes out. Okay, and so this was stated in a different textbook. And there's also, he makes another further statement about the approximation and analysis of finite element analysis. So this is not the do-all, end-all solution to what you were trying to accomplish. This is a tool that you can use to approximate the actual result. And as we go through this class, and as you learn and understand more, you'll appreciate why this is an approximation. So FEA is going to give you an accurate answer to whatever question you ask of it. So you have to make sure that you're asking the right questions and that you are providing the correct properties, geometry, and boundary conditions in order to get the answer that you're looking for. The accuracy itself will depend on the convergence, which is the refinement of the mesh. More elements, more nodes, but you don't necessarily want your whole geometry covered with the same density of nodes and elements as other parts. And so this convergence will help you reduce the error. And the accuracy will also depend on the boundary conditions that you apply and how they're applied. So what can go wrong? There are many reasons why the field results might differ from our actual FEA results. Every variable or piece of data that you are required to put into the system and any assumption you make is a source of error. So what do I mean by that? Well, we're specifying a Young's modulus of 30,000 on this particular piece of material, but if you do enough checking, you can find that the modulus of elasticity for steel can vary 13.8%. So that's 29 times 10 to the 6th to 33 times 10 to the 6th. So depending on which piece of material you have in the field versus what you modeled in FEA, you're going to get a 13% difference. And if you consider materials like injection plastic molding, 3D printing, or casting, where the material isn't as homogeneous and isotropic as steel, then there's more sources for error and changes in parts. Geometry would be another source of error. For this specified size of steel, it might vary by as much as a 32nd of an inch. So, which doesn't sound like a lot, but it can certainly make a difference. The positioning of the material, I mean, we're assuming that that is square to the load, square to the mount. We're assuming that the cross section is orthogonal, and maybe that's not the case in the real world. So there's another source of error. So even this pretty simplistic problem has, can present lots of error and places where the FEA is going to differ from what's actually happening in the real world. So that's part of why we say the pretty pictures are always wrong. So this was a simple part. If we consider a complex part, it's a little hard to tell, but on the overlay you can see that things don't match up quite well. And most of the time, if on complex parts, they're going to check the dimensions where there's mating parts or interface, right? And as long as the rest of it isn't conflicting with the rest of the system, then those dimensions either aren't checked, or if they are out of spec, they're approved because the part's not, the part will still work, it'll still function, but it might fail because it doesn't match what you analyze. So some of the key assumptions that we're making when we deal with FEA analysis, we have 4 primary assumptions that we're going to deal with: geometry, properties, mesh, and boundary conditions. Okay, so the CAD geometry is a template for our mesh, and as I said before, the FEA solver doesn't understand the geometry. It's looking at the nodes and the elements. So we have to make sure that our mesh adequately represents the geometry. And we're saying that it does when we're doing our analysis. The properties, as I mentioned on the previous slide, the modulus of elasticity, if it's varying in the materials that you're using, then obviously you have that amount of error when you're dealing with the loading. So it's always recommended that you kind of bracket your solutions. So you maybe overload it and underload it, or change the modulus from a minimum to a maximum, and see how that affects your part in your analysis, and you can correct for that. The mesh, making sure that it's accurate and that it's what we want to call a good-looking mesh. You're looking for triangles and squares, right? Those are the idealized elements that you're looking for. They're not always going to be exactly that shape, but you want them to approximate that as much as possible. We will also, or you'll also be learning about elements that we're going to use to idealize situations. So we'll have a truss element, we'll have a beam element, we'll have a shell element, and so we're assuming that the element that we're using is approximating the real situation. Boundary conditions are very important, and we have to make sure that we're adequately representing them, because their effect on the displacement and how the model works can be pretty drastic, and it's important that it's correct. So we make assumptions about that. I mean, the connecting rod pictured here operates in a dynamic environment, but how would you model it statically? And you can do that, but you have to make the correct assumptions and put on the correct boundary conditions to be able to do that. It can also be analyzed dynamically, but oftentimes static can be quite sufficient. So, and if you have the incorrect boundary conditions, then sometimes your stresses will be higher or lower than they would normally be. So speaking of static, the other assumption that we'll make about things is that they are going to be linear and that they're in a static state. Okay. And why do we do mostly static? Well, because it's easy and cheaper, faster, and it can provide accurate results for what we're trying to solve. So, and then when we talk about linearity, we're assuming that our material properties follow Hooke's law, right? And that they are in that linear range of the curve for materials. There are some materials that their linear range is pretty small, and so it doesn't take a lot of deflection to get them outside of that range, and so we have to be careful of those. Plastics, 3D printing would be examples of those. We have to also be careful when we're assuming linearity as it relates to geometric concerns. So what do I mean by that? If you have an object that has a large amount of deflection, then it might have to be analyzed in a non-linear way because it's moving too much. Also, materials have geometric stiffening. So this is as the tensile stress increases, the physical part will stiffen, and this is not to be confused with strain hardening, which is a change of properties. So you can compare a non-linear solution with a linear solution, and if there's too much disparity between solutions, then you need to stay with the non-linear solution. But if their solutions are close, then the linear approximation will be fine. For the boundary conditions, we're assuming that when the initial state of the boundary condition is the same as it is after we apply the full load. So as long as there's not too much movement there, we're okay. Where you would get out of the linear range is if you have a component that is maybe not touching some other component, and after you apply the load, it begins to touch that other component. Well, that's obviously going to induce some other forces and stresses, so now you're not in a linear condition anymore. So we can approximate lots of things with linear and static versions, and it's okay. We just have to be aware of the limitations and what we're dealing with. So FEA is a powerful tool for evaluating the structural integrity of a design and making comparisons between various alternatives. FEA is not the do-all, end-all that replaces testing and the use of sound engineering principles. Right? So the qualifications of assumptions is the key to a successful use of FEA analysis, and you must understand the mechanics of the materials, the failure modes, the manufacturing and operating environments this device may encounter, and you must be able to understand the capabilities and limitations of the element type, so whether it's a truss or a beam or a shell, that you are employing to conduct your analysis. And behind every decision there is an assumption that you're making about your FEA analysis, and as long as you remember that and work within that envelope, you will be successful in analyzing your device.